In this paper, we address the problem of in-situ calibration of strain gauge type force torque sensors by proposing nonlinear polynomials as calibration models. Humanoid robots have typically several 6-axis force torque sensors mounted on them, usually on their limbs. The sensors are useful to perform several tasks, including manipulation and locomotion. In addition to estimating the external forces, such as thrust intensities acting on the humanoid robot. The accuracy of the measurements provided by the force torque sensors is essential for the aforementioned tasks. The robotics community is interested in the effect of the calibration on the measurement accuracy of the sensor. Some roboticists have performed in-situ calibration by calibrating the sensor while being mounted on the robot to avoid any changes in the model when mounting and unmounting the sensor. Others have included the temperature of the sensor in the calibration model, since it has a considerable effect, especially on the strain gauge sensors. Further, some researchers have used more complex calibration models than the commonly used affine model, such as the neural networks. In this paper, we extend the calibration model from the commonly used affine model, highlighted in blue, but we keep using polynomials by extending their degrees to quadratic, cubic, and even to higher degrees. The advantage of using polynomials is to account for their sensor nonlinearities not captured by the commonly used affine models, while keeping the model complexity as low as possible. By performing linear regression to the model, we obtain the following linear system of equations, where x is the vector that contains the unknown coefficients highlighted in the previous slide. The optimum value of x is obtained by solving the following quadratic program, which finds the value that minimizes the squared error as shown. Further, we may add a regularization term to also minimize the L1 norm of x. This helps enforcing the sparsity of the obtained coefficients by deriving the small coefficients to zero, which helps in further reducing the model complexity while maintaining the accuracy. The experiment in this paper is focused on the force torque sensors mounted on the robot arm. We designed a dedicated setup to enable attaching weight plates of various weights to the robot. The support is a metal piece mounted on the robot's forearms. Further, we created a URDF model of the robot, along with the mounted weight plates, to be used in the calibration procedure. We moved the robot's arms to vary the applied forces and torques on the sensor as much as possible. Shown on the left, the plots of the three-dimensional forces and torques applied on the force torque sensor mounted on the right arm. The plots show the regions covered in the experiment. The video is accelerated 5 times with respect to the real time. In the video, we show 5 kilograms weight plates attached on the robot. The same experiment is repeated with various weights, from not attaching plates at all to attaching plates in 9 kilograms. Here is a plot showing the three-dimensional forces resulting from repeating the same sequence with different loads to cover as much region as possible. Assuming perfect robot model, negligible sensor noise, and negligible inertia forces since applied motion was slow enough, we compute the expected sensor's measurements. They are computed using the robot's model and its joints positions. The sensor's measurements, including the internal temperature, are considered as input U, and the expected measurements are the model outputs Y. Polynomials of different degrees were tested, from the first degree polynomial, which is the commonly used affine model, up to fifth degree ones. Plotting the forces and torques norms from the validation datasets to show the fitting of various models, first to fifth degree polynomials, obtained by solving the quadratic program optimization. The table reports also the model complexity, which is indicated by the number of coefficients in the model. We can see that the fourth degree polynomial has achieved the highest accuracy, with the root mean square error highlighted in blue. In another test, we focus on fourth degree polynomials whose coefficients are obtained using quadratic programming with L1 norm regularization, while varying the weight lambda. The table also reports the model complexity, which is indicated by the number of effective coefficients with values higher than 10 to the power minus 9. The more we increase lambda, the more we suppress the non-important coefficients, reducing model complexity. We can see that the model with lambda equals 50 achieves the highest accuracy among the others. Thank you.